Okay, if you've been following the course up until now, we've been dealing with substitution reactions. And I want to look at this reaction that I've laid out over here and see how sometimes things that look like they could be a substitution reaction are not, and that there's something else that might occur. So if we look at this reaction over here, we're not too sure what the product might be. What we're going to do is we need to kind of figure out, well, the only thing that we know that we can think about at the moment is that it could possibly be a substitution reaction. So if we're looking at that, we're going to be using the acronym SEEN. And the first thing that we ask ourselves when we're looking at this is, if it's a substitution reaction, the electrophile that we have should be something that has a good leaving group on it. And, well, that we definitely have. We've got a carbon, which is sp3 hybridized. It's got a good leaving group on it. And so that's looking quite nice for it to be a substitution reaction. Do we have a nucleophile? Well, the answer to that is yes. We've got an O- over here. And O- is a very strong nucleophile, in fact. So we do have that. We've got a nice strong nucleophile over there. So that's also looking good. And in terms of being a strong nucleophile, it's certainly something that would be pushing towards an SN2 type of reaction. If we consider the electrophile, we see in terms of sterics of the electrophile very sterically unhindered. And also the chance of making a carbocation over here, primary carbocation, is going to be absolutely terrible. So we are pushing all the way to a SN2 type of reaction as well. I haven't actually put anything else in here, but I could fill in the rest. We've got solvent and we've got some, the reaction conditions involve room temperature, and all of that is again going totally towards the environmental aspects are looking very much towards an SN2 reaction. So looking at this from the information that we've learned so far, the temptation here would be to do an SN2 reaction, which is this negative charge of the nucleophile would come into this carbon over here, kick out the leaving group, and we would get this product over here substituted. So based on what we know, this is what should happen. However, this absolutely does not happen. This reaction is not at all going to give that product. Instead, the product that forms looks totally different. This is what we get as a final product. So what has happened in this reaction over here? Well, we can see that the leaving group has left, so the bromine has left in some way. But we can also, if we look very carefully, what we will have noticed is in the product over here, clearly the bromine left from over here. This carbon over here has two hydrogens, which are over there. There's two hydrogen atoms. But this carbon only has one hydrogen atom on it. And over here, there are two hydrogens. So one of these hydrogens has also disappeared. And in fact, we can see that hydrogen in the product of the alcohol that's been formed over there. And so there's something else that's going on over here. It's this nucleophile over here hasn't attacked as a nucleophile. Rather, it has acted as a base. It has picked up this proton over here, and the electrons over there have kicked in, and the leaving group is left. I'll come back to the mechanism again, but I want us to just have a look at another example, which we might want to look at first of all from a substitution, and it doesn't do that. So here's this example. All right, so if we're looking at this example over here, and we're analyzing it from our acronym, looking at all the different components of it, and up until now, we've only had to consider substitution reactions, so that's what we're going to think of with that. So in this one over here, it's one of those cases that ends up being a little bit more complicated. Do we have an electrophile? Well, initially, the problem with answering whether we have an electrophile is that we don't. We don't have a good leaving group over here. And that is the first one of those sort of problem areas where we need to go and look at the environment. And the environment says that we do have a strong acid present. A strong acid would protonate this alcohol over here, turning it into a good leaving group that could leave. So actually, although we don't have it directly, we could, in a step, using this tosic acid over there, we can imagine a protonation occurring and giving us something that looks like this over there, and then we're left behind with the TSO minus. So at this point, things are looking quite promising in terms of the substitution reaction that we've seen so far. We have got an electrophile and we do have a nucleophile over there. So we've got this electrophile. That's looking good. In terms of the substitution reaction, we're looking at sterics and we're looking at the carbocation. Now, in terms of sterics, we have a secondary leaving group. So actually, in terms of a decision between SN1 and SN2, we don't really know. They both of them are possibilities. Then we look at the carbocation. The carbocation that would form over here, if this left, would be a secondary carbocation, but it would be a lilac. It's next door to a double bond. And that is starting to look a little bit like we are favoring an SN1 reaction. Then we look at the conditions and we see that we're heating up this reaction quite a bit. And in heating up this reaction, that's also something that typically points towards an SN1 reaction. The nucleophile is an O-. This is a delocalized O-, so it's not a strong nucleophile that we'd normally sort of associate with a nucleophile. Is definitely not looking like an SN2 from that point of view, and more pointing towards an SN1. So this mechanism over here, or from what we've looked at, we would say, okay, we're working this out. We've got this nucleophile over there. This, forgot the plus charge over there, is a good leaving group. It's going to be SN1, so this is going to want to leave. We're going to get the carbocation, and then what we're going to predict is the TSO- is going to come in and attack over there, and we would get this product being formed. And that would again be wrong. This reaction does not occur like that. In fact, what happens, the product of this reaction ends up being a new alkene. So if we look at this over here, again, something that's weird that's been happening is that we have, what it looks like is we've eliminated water. So we have two protons over here, and it's like this H and this OH over here have combined, and we've eliminated, and we've got water over there. Sorry, of course this will be protonated. The acid is just acting as a catalyst. All right, so both of these, clearly something else is happening. So it's no longer a substitution reaction, but rather an elimination reaction. And so what we're going to have to do is we're going to have to just look at the big picture of elimination reactions. What do they look like, and how do we find out about them? And then we're going to have to consider what are the differences between a substitution and an elimination. And we've got to figure out what is going to be preferred in a reaction. And we'll do that in the next lecture. But for now, I just want to look at a general scheme of elimination reactions. All right, so this is going to be a general scheme of elimination reactions. And for an elimination reaction to occur, what tends to happen is that we no longer have what we call a nucleophile, but rather what we call a base. And what the base does is it acts as a base because it picks up a proton. And so from a mechanistic point of view, this is one of the mechanisms. From a mechanistic point of view, the minus will come and pick up a proton. The electrons in the carbon-hydrogen bond are going to go in and donate to form the pi bond, and our leaving group leaves like this. And so the result of that is the formation of an alkene. And in both cases that I've shown you already, elimination reactions always result in an alkene. The base picks up that proton, and there will also be the leaving group which left, and the leaving group is almost always negatively charged, not always, just depending on the base and the type of leaving group that we had. All right, so perhaps taking analogies a little bit too far, in our substitution reactions, we spoke about substitution reactions being like a relationship where a nucleophile comes in, or the new guy comes in, and the loser guy leaves when looking at a girl who's having this relationship. In elimination reactions, it's perhaps maybe taking the analogy a little bit too far here, but this is a case of where the new guy that comes in is not really a great guy. He's a bit of a bad guy. You might use another word that starts with B, but he's a bad guy who comes in and he kind of wrecks the whole thing for the girl and leaves her changed in some way, causes some sort of emotional damage or something. So yeah, maybe taking those analogies a little bit too far, but an elimination reaction is this type of affair. We're not having the base acting as a nucleophile, forming a new bond with the molecule, but rather just acting as a base that is going to pick up a proton. And that's going to be one of the tricky things that we're going to have to look at. Let's just look at the features that are important for an elimination reaction, though. The first feature is, much like substitution reactions, the carbon atom here needs to be a saturated or sp3 hybridized carbon. Remember that these two words are effectively synonymous to each other. They are identical. This is a bit of tautology because a saturated carbon has no double bonds in it, and an sp3 carbon has no double bonds at all, or no pi bonds in it. So we could use either thing. We can call it a saturated carbon or an sp3 carbon. It's not that these are two different things. The other thing that is quite important, and this is the new thing that we've seen, is that we must have what we call beta hydrogens. What do we mean by beta hydrogen? What the language that we use here is that the leading group is on the alpha position, and the carbon next door, which could be on either side, is the beta position. So this hydrogen is on the carbon which is beta to the leaving group. That is an important feature. If you don't have that, an elimination reaction cannot happen at all. Now, elimination reactions, just like substitution reactions, happen via two mechanisms. And the mechanisms are really so closely interrelated to SN1 and SN2 that I don't have to go into too much detail about that. So we essentially have two types. The one is E1 and the other one is E2. Now, the mechanism that I've drawn at the top over there is the E2 mechanism. And E2 stands for elimination bimolecular. This is the reaction mechanism that takes place in one step. So this is just like an SN2 reaction. We know it takes place in one step because when we do the rate and the kinetic experiments on reactions that involve E2 mechanisms, they are affected by both the concentration of the base and the concentration of the molecule with the leaving group. So this tells us about the mechanism, and what it tells us is that this mechanism occurs in one step. It all happens at the same time, and so what we've drawn over here is the equivalent of that. The base picks up the proton, these electrons leave, and it all happens in the same time. The consequences of that we'll explore in a future lecture, just like SN2. There are stereochemical consequences, but we'll explore that in a future lecture. This is one of the reasons why we need to know the differences between the two. An E1 mechanism I haven't shown you over here yet, but this one is the opposite of, just like an SN1 reaction. So we'll call this as an elimination unimolecular. And the key feature here is that it takes place in two steps. I'll draw the mechanism out now, but the two-step is just like an SN1 reaction, and that is that the leading group needs to leave first, and we get a carbocation, and then the base comes in, and we form the double bond. I'll draw that out now. But the other thing is connected to the kinetics. Why we know that is that this reaction is not affected at all by the concentration of the base. All right, so an E1 reaction, if we had to just draw out the mechanism very simplistically, I'll just squeeze it in over here. The first step is going to be how the leaving group needs to leave. So the leaving group will leave somehow. That generates our carbocation. Sorry, I've switched things around there. And then the next step is that we're going to have a base. Notice I'm just using a lone pair here. We're going to see why later, but it's typically because the bases here are weaker, but we'll get back to that. And it picks up the H and we form our alkene. Like that over there. All right, so that's a two-step process. So that's all we need to do in terms of just an introduction in terms of elimination reactions. It might seem a little bit scary right now because it introduces a whole new thing that we got to consider in terms of when is an elimination reaction occurring and when is a substitution reaction is going to occur. There are a whole lot of very simple and obvious rules that we'll explore in the next lecture, so don't be worried about that right now. Right now, the key thing is just to recognize the potential, the possibility of an elimination occurring. Look for the features such as beta hydrogens and a saturated carbon, and just understand the motif of this thing. And we'll see you in the next lecture.